So we've seen the singing bowl, and that when it's excited, it produces sound, which disturbs the airwaves around it. Those waves travel through the air and into our ears, causing our ear membrane, the tympani of our ear, to vibrate, and our brain then perceives pitch and sound. The simplest form of the sound emitted from the singing bowl would be a single sine wave, such as the one shown here. Now, the singing bowl issued not just one of these sine waves, but also many other sine waves that are multiples of this sine wave in terms of frequency. So you might see this sine wave here, and one that goes twice as fast, and 3 times as fast, 4, 5, 6, and so on. And it's the relative strengths of each of those overtones, each of those faster versions of the sine wave, that give each sound its own particular characteristic. Why does a trombone sound different than a violin, even when they're playing the same note? It has to do with the characteristics of these overtones, the relative strengths that make each of these instruments sound different. So if we look at a sine wave as the simplest form of this kind of energy, let's think about just a single sine wave, which would sound like a very pure tone. The sine wave is shown in red, and in gray we see an approximation of the sine wave. We can't really represent a complete sine wave on a computer. We need to find a discrete representation for it, one that takes up finite space. We do that by sampling points along the sine wave, and where the gray area intersects the red line, those are the points we actually transmit to represent the sine wave. We'll see more of this coming up soon. In terms of sound, these sine waves have 2 fundamental properties that we perceive. The first is pitch. The pitch of the note may sound high or may sound low. What is it that makes it sound one way or the other? It's the frequency at which the sine wave is oscillating. So if the sine wave is oscillating slowly, we perceive a low pitch. If it's oscillating more quickly, we perceive a higher pitch. We measure the pitch of the sine wave in terms of its frequency of oscillation per second. This is often abbreviated as hertz. It turns out that 440 cycles per second, or 440 hertz, is the standard for concert A, which is the A just above middle C on a piano. So the question we would ask in terms of pitch is, how many cycles per second do we see from a given sine wave? If we look at the frequency of a sine wave, it may oscillate slowly, such as the top curve shown here, which is about 20 hertz, 20 cycles per second. This turns out to be near the bottom range of what we humans can perceive in terms of pitch. Shown below that is a sine wave that oscillates at 440 hertz, about 20 times as fast, and that represents concert A, the A above middle C. The other dimension of sound that we perceive, besides the pitch or frequency, is the volume. How loud is the sound? A given sine wave may oscillate the same number of times per second as some other sine wave, but one sine wave may rise higher and dip lower even at the same frequency. This increase in amplitude corresponds to an increase in volume, and we can perceive that as well. When we think about sound and pitch in this course, we're going to encode each note, let's say of the piano, or any kind of fixed-pitched instrument, as a simple integer. And we let concert A be represented by the integer 0. Any pitch above or below is represented by an integer higher or lower than 0. We see a piano keyboard represented here, and the white notes of the piano going from concert A to the A above it are labeled 0, 2, 3, 5, 7, 8, 10, and 12. The spacing between these integers is different because of the black keys that interpose between the white keys. In looking at the difference between A and the B right next to it, there's an A sharp or a B flat that interposes, and so the displacement between A and B is therefore 2. But in stepping from the B to the C, a half step on the piano, there is no black note, so we increment the integer by a single value to reach 3 at high C. So we're able to go from one pitch to the other by starting at concert A and calling that 0, then counting the number of half steps, the number of steps that reach the next black or white key, in succession, incrementing the number each time to reach the desired frequency. If we look at pitch, in terms of frequency, concert A oscillates at 440 times a second. An octave higher than that, the A above that, would oscillate twice as fast, at 880 cycles per second. In effect, we want to be able to take 12 steps from one A to the next A and in getting to the higher A, be able to oscillate twice as fast. When we talked about the pitch of the singing bowl, we were able to think about multiples, integral multiples of a given frequency that issue the overtones we hear from the singing bowl. Look at the difference here between A, represented by pitch 0, and E, represented by pitch 7. The frequency at pitch 7 ought to be 1.5 times the A if it were an overtone. So, if concert A is 440, the pitch at offset 7 ought to be 440 plus 220, or 660. But we see it's not 660. It's actually slightly flat of that at 659.26. So why is this? If we decide to take steps between the A at 440 Hertz and the A above it, we would like to reach a factor of 2 by the time we get to the 880. In order to do that and to make each of the steps even, we need to make each step from one pitch to the next have a ratio of the 12th root of 2. So going from 440 to 466, going from the A to the B flat or A sharp, the ratio of those two frequencies is roughly the 12th root of 2. If we take 12 steps, each time multiplying by the 12th root of 2, by the time we take 12 such steps, the radical disappears and we get a factor of 2 to go from 440 to 880. So in even temperament, where every pair of adjacent notes has the same frequency ratio, that ratio is exactly the 12th root of 2. On a more continuous instrument, such as the violin or cello, a player can make small differences in the way the string is played and achieve the fractional multiples that we saw from the singing bowl. So we will be representing pitch using these integers. Starting from 0 and counting up, we get higher in the scale from A to A flat, from A to A sharp, which is also B flat, to B natural and to C. But these numbers can also become negative as we count down from the A. So to go from A to A flat, a half step down, we would use -1. To go from the A flat to the G, we would use -2, and so on.